Hey guys, this is Anas Hamoudni from Math World and welcome to this new video. Today's video will be about the proof of the uncountability of real numbers. So basically what a countable set is. So let's start by defining a set of elements. So we call them so basically A, B and C. And what a countable set is basically the fact that we can just link each element and enumerate the set. So basically link each element to a integer. So basically A is the first element, B is the second element, and C is the third element. So this set is called countable because there's a function between this set and the set of integers which counts the elements of the set. Thus we called the set a countable one. What we're going to show today is that the set of real numbers, well, it's not countable because we can't find a bijection between the set of real numbers and the set of integers. So without further ado, let's start. So basically the proof will be based on a contradiction. So we'll start by assuming that we have already the bijection between the real numbers and the set of integers. So we start by just enumerating all the numbers, all the real numbers. But for the sake of simplicity, we will just prove this to the numbers between 0 and 1. So in the 0-1 interval. Because basically the proof will be focusing on the infinity of decimals, and we will not focus on the entire parts. So let's assume that 0-1 interval is countable. So basically that will assume that there is a first element which will start by 0. So basically you start by 0. Then the first decimal we'll call it A11. So basically the first row, first column. So second one A12, sorry, A12, so the first row, so A12, third element A13, until so infinity. So we'll continue doing this. So basically we reach some part where there's a element A1I and etc. So this is suppose that we already have the first element in the 0-1 interval, and assume that we know the second element, so in the list. So, and we'll just we'll be noting it as 0.1 A21, so the second row, first column, A22, A23, and going on until A2I, and continuing after that. So basically we assume that there is a bijection. That means that we can go further and enumerate first element, second element, third element, fourth element, fifth element, 10th element, etc. So until infinity, because actually there's a bijection, but the set of elements of real numbers between 0 and 1, we know that it is infinite. And our goal here is to prove, not to prove that it is infinite, but to prove that it can't be countable. So we can't count. And if we continue here, we'll reach some parts where there's an ith element or I would say a jth element. So it will be 0, A, G, 1 until we reach A, G, G, and we continue. So we reach A, G, G, and we continue to A, G, I, and we go into infinity. So we go into infinity. And here we are at the jth elements, but this will continue. So this will continue infinitely many times, and we enumerate infinitely many real numbers between 0 and 1. So we'll count infinitely many elements between 0 and 1. And now comes the part of the proof which is interesting. So basically, what Cantor, actually the founder of this proof method, is actually trying to find a contradiction in this hypothesis of the bijection between real numbers and the set of integers. And he wanted to find an element which wasn't counted. So we are assuming here that we counted all the elements, but what Cantor wanted to do is that he could find a element which is not counted in this list. So we reach that, but let me just give you a rule by which he found the missing element. So let's here just put 0. So the following number to 0 in decimals is 1, and the following one is 2. So we continue like that until reaching the 9. But now if we add 1, we'll not go to 10. So we'll not go to 10. Instead, we should come back to 0, because these are the decimals, so they are different, and we don't reach 10, but reach 0. So this remark here, we'll use it in the proof. So in order to find the missing element, we'll use this technique here. And now what Cantor has done is that he focused on the diagonal. So basically an element which will be missed here is an element which differs from the first one, the second one, and the jth one, and the ith one, etc. So an element which Cantor has found is an element which has, well, as a starting point, the diagonal. So the diagonal is A11, A22, AJJ, and etc. until infinity. To guarantee that our element is different from the first element and the second element and the third element and etc., we'll take each term of the diagonal and we'll add 1 to it. So basically our number will have 0 point, first element of the first number plus 1, second decimal of the second element plus 1, etc. We'll add plus 1 to each element. And of course, if we find 9, then the plus 1 will be 0. So the element will be 0. And what we find here is that the element which was constructed by Cantor based on the diagonal is different from the first element because they differ in the first decimal, and is different from the second element because they differ in the second decimal, and is different from the jth element because they differ in the jth decimal, and etc. This element is different from any number in this list, and so this element isn't in this list. So this element is basically this one. So let's just write it here, 0 point. So basically A11, will add 1 to it. 822 will add 1 to it. 833 will add 1 to it, etc., etc. So, and we go infinitely this way. So this element here, well, this element here isn't in the list, and so we found that by assuming that there is a bijection, so that we can count each element and not miss anyone, we found that we can always construct an element, which is this one, which is not contained in the list. So this is a contradiction, and this proves that actually the real set, so the set of real numbers, actually has infinitely more elements than the set of integers. So basically, the infinity of, well, here we just assumed the 0, 1 set, so we used only the 0, 1 set. So the infinity of 0, 1 is bigger than the infinity of, well, the infinity of the integers. That means that the infinite set 0, 1 contains more elements than the set of integers. Well, that was very unpredictable. And Cantor proves this result actually by the diagonalization proof. So this was today's video. Thank you for watching, and goodbye.